Welcome to Module 2 of Beyond Arduino. In Module 1, we learned how writing a simple program switched on an LED. But today, we are going to ask a much bigger question. What is actually happening inside the microcontroller? When we write a program and upload it to an Arduino, where does that program go? How does the CPU find our instructions? Where are variables stored? How do timers, ADCs, and communication modules work together? And perhaps the most important question of all, how do engineers understand systems that are much more complicated than an Arduino? The answer is not memorization. Engineers build mental models.
We create a movie in our minds that explains how information moves and how different parts work together. In this module, we will start building that bigger mental movie. We will move beyond simply connecting components and begin to understand the architecture of real microcontrollers. We will also discover one of the most important tools of every engineer, the datasheet. By the end of this module, you will see a microcontroller not as a mysterious black box, but as a complete system whose parts work together in harmony. So, let's begin our journey beyond the LED and start thinking like real embedded engineers.
Before we move into new ideas, let us quickly review something we learned in Module 1. We learned how a simple line of code can make an LED turn on. At first, it may seem like magic, but now we know that there is a clear sequence of events happening inside the microcontroller. First, the CPU makes a decision. The CPU executes our program and decides that the LED should turn on. Next, the CPU writes a value into an output register. In this case, it writes a high, which means a logic 1. The register temporarily stores that information inside the chip. Then, that value is sent to the physical output pin. On an Arduino Uno, this example uses pin 13. The pin outputs a high voltage, approximately 5 volts. Current now flows through the LED circuit. And finally, the LED turns on. So the LED does not light up by magic. The CPU makes a decision. The register stores that decision. The pin sends the signal to the outside world, and the LED responds. This simple process is actually the foundation of all embedded systems. The same basic ideas that turn on a tiny LED are also used to control sensors, motors, robots, industrial machines, and many other complex systems. Understanding this simple journey will help us build much bigger mental models in the modules ahead. So far, we focused on switching an LED on. But real embedded systems do much more than that. They solve real problems in the world around us. Engineers use embedded systems to sense, decide, act, and communicate. To do that, we need several important building blocks. The first building block is sensors. Sensors allow a system to understand its environment. They can measure temperature, light, distance, pressure, and many other physical quantities. The second building block is motors and actuators. These are the parts that make things move and happen. Examples include DC motors, servo motors, relays, and solenoids. The third building block is communication. Embedded systems rarely work alone. They need to exchange information with other devices using technologies such as UART, I2C, SPI, Bluetooth, and Wi-Fi. The fourth building block is timers and counters. These help us measure time, create delays, generate PWM signals, and keep track of events. And finally, we have interrupts. Interrupts allow a system to react immediately when something important happens, such as a button press, a sensor trigger, or a fault condition. These 5 building blocks are at the heart of almost every embedded system. They work together to sense, decide, act, and communicate. You will find them in smart homes, robots, medical devices, drones, automobiles, and industrial automation systems. The better you understand these building blocks, the better engineer and problem solver you will become. Everything begins with something very small. For many engineers, that journey starts with a simple LED. Learning to turn an LED on and off may seem like a tiny achievement, but it is actually the first step into the world of embedded systems. The next step is working with sensors. Sensors allow our systems to understand the real world. They can measure distance, temperature, light, pressure, and many other physical quantities. Once a system can sense its environment, it becomes aware. Then we learn to control motors and actuators. Now our systems can do more than observe. They can act on the real world and create movement and motion. When we combine sensors, motors, computation, and communication, we can build robots. Robots are intelligent machines that can sense, think, and act. The same principles scale even further. In factory automation, engineers build systems that improve productivity, increase safety, and save resources. And in aircraft and space systems, these technologies help us fly, explore space, and shape the future. The important lesson is that the same core building blocks exist in all these systems. Every system contains a microcontroller or computer that acts as the brain. It receives information from sensors. It uses logic to make decisions. It controls actuators to create actions. It communicates with other systems. And it requires power to bring everything to life. These simple building blocks, working together, create endless possibilities. So never underestimate the importance of learning the fundamentals. Understanding the small things is how engineers eventually build the big things. In the last slide, we saw that the same building blocks can take us from a simple LED all the way to robots, factories, and even aircraft systems. But now we face a much bigger question. How can one tiny chip do all of this? Think about it for a moment. The same kind of microcontroller can control a smart home, where sensors measure temperature and devices can be controlled remotely. It can power medical equipment, where accuracy, safety, and reliability are absolutely critical. It can drive robots that move precisely, sense their environment, and make intelligent decisions. It can fly drones, performing navigation and real-time control hundreds of times every second. It can run factory automation systems that monitor processes and coordinate machines with incredible precision. And it can support modern automotive systems that manage engines, safety features, and smart technologies. One tiny chip. So many incredible applications. How is that possible? What is really inside this little black box that gives it such amazing capabilities? This is exactly the question that engineers ask. Great engineers are curious. They do not treat technology as magic. They open the black box and try to understand what is happening inside. That is what we are going to do in this module. We will look inside the microcontroller, discover its different parts, understand how they work together, and build a much bigger mental movie of the entire system. Because to become a great engineer, we must understand not only what a system does, but also what is really happening inside.
Now, let us do what every engineer loves to do. Let us open the black box. At first, a microcontroller looks like a single mysterious device. But once we look inside, we discover something very important. A microcontroller is not one thing. It is actually a collection of many specialized building blocks, all working together as a team. Each block has its own job. The CPU is the brain. It makes decisions and executes instructions. Flash memory stores our program permanently, even when the power is turned off. RAM stores temporary information and variables while the program is running. Registers are the CPU's fast working area, where important values are kept for immediate use. Timers help the system measure time, generate delays, create PWM signals, and count events. Communication modules, such as UART, allow the microcontroller to talk to other devices.
The ADC converts real-world analog signals, such as temperature, light, or voltage, into digital values that the CPU can understand. And finally, the I/O pins act as doors between the microcontroller and the outside world. They allow the chip to sense, control, and interact with real systems. When all these building blocks work together, something amazing happens. The system can sense the world around it. It can think and make decisions. It can act and control machines. It can communicate with other systems. And it can solve real problems in the physical world. Over the next few lessons, we will meet each of these building blocks one by one. We will understand what each part does, why it exists, and most importantly, how all of them work together to create intelligent embedded systems. Now, let us meet the most important building block inside the microcontroller, the CPU. The CPU is the brain of the entire system. Just like our brain reads information, makes decisions, and tells our body what to do, the CPU does exactly the same thing inside a microcontroller. Its first job is to read instructions from memory. Those instructions are the program that we wrote. The CPU follows those instructions one by one, step by step. Next, it processes data. It looks at sensor values, checks variables, performs calculations, and decides what should happen next. Then, it controls all the other building blocks inside the chip. It communicates with memory. It uses peripherals such as timers, ADCs, and communication modules. And it sends commands to the I/O pins that connect to the real world. You can think of the CPU as a factory manager. The manager reads the production plan, makes decisions, gives instructions to workers, and ensures that everything works together smoothly. The CPU does exactly the same thing. It reads the program, makes decisions, controls the different modules, and keeps the entire system running. In simple words, the process is very straightforward. An instruction comes in, the CPU thinks about it, and then an action happens. This cycle repeats millions, or even hundreds of millions of times every second. Without the CPU, none of the other parts know what to do. The CPU is the thinker, the planner, and the controller of the entire microcontroller. It is truly the decision maker at the heart of every embedded system.